to Guido, who's going to introduce the session.
Okay. Is this visible now? Yes?
Yes, that's great.
Okay, brilliant. Yeah, thank you very much. Good morning. Welcome actually to this third and last session of webinars actually on human-robot interaction. This has been organized by John Dukes, our RAIN program manager, and myself. Within today's session, I will just simply remind you at first again of the webinars we have been organizing. Then I will introduce or reintroduce the idea of the HRI workshop. We had good discussions after also some feedback from colleagues on the HRI workshop, and I will introduce to you actually how we slightly reshaped actually the HRI workshop. Then we will have three topical actually talks by Peter Scarf, Ingmo Young, and Alex Smith on various issues of human-robot interaction and within obviously robotics for extreme conditions. And at the end, we would like to leave possibly some minutes for short discussions, possibly on feedback, not only on the talks, but also on our plans. So just to see actually if you have any additional ideas of what we want to do here. So again, as a reminder, there have been obviously two HRI seminars, one actually on the 7th of May under the lead of Professor Varish, various issues on HRI such as perception, communication and decision making. On the 28th of May, we had another webinar under my lead, and we were talking about actually human factors. That was by Emily Collins. Azan actually Catley was talking about teleoperation, and Evan Lopez about the prediction of human actions. Today, we will have actually a joined up actually session of RAIN and NCNR researchers, also again on HRI, specifically on haptics, teleoperation, and also variable autonomy. And again, obviously, our idea is that we would like to use this as a kickoff to organize a UK-wide workshop on human-robot interaction. We do appreciate that actually we want to show you actually also our practical outcomes, obviously more actively in our teleoperation demonstrator, due to the COVID-19 situation that is not so easily achieved. Hence, actually, our approach of engaging with you in this HRI workshop at the end of August. Again, it will be web-based. Initially, we thought it might be good to have it over 2 days, but then the opportunity of doing it web-based gives us actually the possibility to engage with you actually more on half days in 3 days, and I will explain to you actually how we're going to do this. So we would like to engage across the community in the UK, and in that respect actually the first day will be very much an industry focus, about half a day. The second day will be very much more a university focus, disseminating actually the results of academia to you. And then we would like to keep possibly a 1 or 2 day gap, collecting actually feedback from you in terms actually of what we had discussed before. And the last day actually will be very much a joined up discussion, strategically thinking about how we can go forward, obviously beyond actually the hubs on robotics in extreme conditions and HRI. So we would like to have in the first day pretty much ideas from industry on their future view on human-robot interaction, targeted talks, question and answer panels, and so on. And that will be then taken forward on the second day, more on academics, talks, theme-oriented actually sessions on virtual reality, augmented reality, teleoperation, haptics, shared control, human-robot interaction communications. So how do we communicate between a human and a robot? Human factors in general, because one needs to look at the larger point of view, and certainly trustworthiness of the technology, of the methods we are developing. And that, again, obviously with a 2-day gap actually, or 1-day gap actually in between the 3rd day, half day, where we can discuss obviously and taking feedback actually from the first 2 days. Again, the wider objectives are effectively to create a roadmap on HRI and robotics in extreme conditions, but certainly also in not only extreme conditions, and then engage with funders within these meetings and preparing actually and planning actually for this roadmap. So following actually my short introduction, there will be then obviously the talks, but after these talks, we would like to hear pretty much your opinion, and maybe actually we can shortly engage on that actually after these 3 talks today. So thank you very much. I would like to hand over straight to Peter, and he will hold obviously a talk today on haptics.
Okay, cool. Thank you. Just make sure. Can everyone see my screen okay?
Yeah, that's great, Peter.
Excellent, cool. So today I'm going to be talking to you about understanding sensory motor optimization of a bimanual telerobotic system. And by way of a few brief introductions, I'm Peter. I'm based at the University of Reading. I run the Vision and Haptics Laboratory there, and work in the lab kind of straddles the boundary between perceptual psychology and engineering, in particular virtual reality and haptic robotics. Collaborates a lot externally, for example, with Facebook Reality Labs and the NHS. The co-investigator on the grant is Professor William Harwin. He's also based at University of Reading and also RACE. William's an expert in haptics and rehabilitation robotics, and also wearables for healthcare. You can see a range of the areas he works in here. And then finally, I'd like to introduce Julie Skivic, who's the postdoctoral researcher working on the RAIN grant in my lab. Julie's got a background in electronic engineering and also completed a PhD in my lab. So our actual project unfortunately started at a rather bad time. We started in March, and we're running until March next year. So this was just before COVID and the lockdown. So what I'm going to be doing today is I'm going to be giving you an overview of the project's aims and a bit of the context, and then hopefully we'll be presenting some of our results of the research at the planned UK-wide workshop, which was mentioned. So obviously there are numerous environments in which humans are unable to access or work on directly due to these being remote or hazardous in nature. And whilst huge strides are being made in autonomous systems, for the foreseeable future, it's going to be necessary to have a human in the control loop, especially for more complex operations. And obviously, typically this is done via some kind of telerobotic system. So here's just a picture of the mascot system at RACE and a user using that system. So the key problem here is that telerobotic systems typically impose complex sensory motor transforms on the user. And this has a few key problems. First of all, it makes such a system quite difficult to use. It can take a long time to learn how to use a system such as this. And as a result, using such a system can be expensive both in time and money. So the key to a teleoperation system is making working in the remote environment as effortless as you really are there yourself. People use this kind of phrase that the system should be transparent to the user. So here you have just a simple schematic from Barfield. So we have our user in a remote location operating some kind of hardware in the environment, interacting with real-world objects, and the user is getting some kind of sensory feedback from the robotic device, which they're using to control it. So the key thing here is that the user has to build some kind of mental model as to the relationship between their own movements and the movements of the robot. So in some senses, the ideal situation is that the kinematics of the user and the kinematics of the robot have a one-to-one mapping with one another. However, this is clearly not possible in most instances. So why is this a problem? Well, the brain is just a fancy computer in effect, a neural computer, but a fancy computer nonetheless. And it takes in information in the form of sensory inputs, does some kind of computation on those sensory inputs, which results in some kind of motor output. And that motor output might be something very simple, such as picking up an object in everyday life, or indeed it might be something much more complicated, such as using a teleoperation system. And there's actually a lot of clear evidence that in programming sensory motor actions, the human brain effectively computes an internal forward model of the action in order to predict the sensory consequences of that action. And then the brain compares this to the actual sensory feedback from doing the action. And this comparison allows the brain and the user to learn how to do a task and indeed improve a task over time. And we can kind of see that in this schematic here. So the brain produces a motor command which is sent to the sensory motor system. The action is performed and the observer gains some kind of sensory feedback. And the key thing here is that actually what happens in the brain is the motor command is duplicated into what is called an efference copy. And this is used to predict what the sensory consequences of the action will be. And then the two are compared and some sort of sensory discrepancy is computed. And in doing this, this allows the user to improve at the task over time. The key thing is that there's a huge amount of evidence that shows that imposing sensory motor transforms negatively impacts performance, slows learning, and indeed requires some kind of adaptation procedure over time. This is actually a very kind of engineering type focused model, even though it's modeling brain processing. And some of you may be familiar with models such as this, the iterative learning model. And this is used in a wide range of areas of industry and engineering. But the key thing here again is that through comparing a prediction to an error, one can improve performance over time of such a system. So let's go back to where we started. So this was our example. So what's the problem to be solved here? Well, clearly, in most telepresence systems, there's a mismatch between the kinematics of the human, so the human operator in the control room, and the kinematics of the robot in the remote environment. And this obviously makes it very hard for the user to predict the sensory consequences of what their action is going to be. They don't know how their actions map onto actions of the robot. A second issue is that there's an issue with this other part of the loop here. That is, it's really difficult for the human user to get precise sensory feedback as to what the results of that actions were. So for example, here, an operator is having to track their movements over multiple screens. And in a hazardous environment, these screens might be placed at very odd angles relative to the user and or provide impoverished information. A final problem is that the user doesn't have access to a lot of information that they normally would. For example, there's no stereo vision here from the remote environment. And indeed, as the observer moves the head, the user moves the head, these views don't update as they would naturally. So that's kind of the problem we're kind of looking to investigate. So now for a few project specifics. So our aim here is to systematically map out the effects of mismatched physical and visible workspaces on the efficiency of a bimanual movement, and this will be in a visual haptic telerobotic environment. So this is the kind of setup we're going to be using. So we have a set of custom-made haptic robotic devices. For those who are familiar with these types of things, these are very similar to the phantom force feedback devices. We have 2 devices per hand, so we're able to do bimanual manipulation with 2 points of contact per hand. The visible information is going to be provided by an Oculus headset, so people will be in an immersive virtual reality environment. And a key thing is we're going to be hooking these 2 systems up by our Vicon system, which will allow us to align the haptic and the visual environment to millimeter precision. And this is super important because this then allows us to investigate the effects of adding sensory motor transforms between these 2 spaces. So as I mentioned, the ideal situation is that there's a one-to-one mapping between the physical and virtual workspaces. So here we just have a toy example of a 3D space, an observer in that space and a bunch of objects, and there's a one-to-one mapping between these 2 spaces. However, in a telepresence system, one can have a whole range of transforms. For example, the virtual space might be translated relative to the physical space, rotated relative to the physical space. There might be some kind of scaling or gain between the movements of the user and the movements of the robotic device. Or indeed, what is more likely is there'll be some kind of complex combination of these transforms. So this is what we're going to be doing, kind of parametrically introducing these transforms into our system and measuring the effects. The task we're going to be using is probably familiar to a lot of people, is a post-operational clean-out type task. And we're collaborating very closely with RACE, especially in my Glovebox demonstrator, to kind of build a very real-world task. The task will involve the bimanual manipulation of objects, passing of objects between the 2 hands, because we're able to do that in our system, and then also posting these objects out for a slot. So a very kind of familiar task, presumably to a lot of you. So what characterizes good movement performance? How are we going to kind of measure the effect of these transforms? Well, the other thing is no one really knows exactly what characterizes a good movement. There are obviously some ideas. For example, a movement which is carried out quickly and efficiently would probably be better than a movement carried out slowly. There are also some metrics, for example, the smoothness of a movement. So if you have fewer velocity peaks in your movement profile, it's generally considered to be better as a smooth movement. Similarly, if you're carrying out a repeated task over time, the variance of endpoint parameters of that task is a good measure of efficiency. And there are indeed these kind of larger scale optimal models which attempt to kind of optimize movement parameters. So whilst the telepresence system in effect offers the ability to kind of build beyond the efficiency of natural movements, currently telepresence systems are far away from just the elegance of an everyday movement, such as reaching out to pick up an object. So as such, what we're going to be using in our project is we're going to be using real-world movements as effectively the gold standard to which to compare telepresent movements. So here's a quick schematic of our task. So we're going to be using a post-operational clean-out type task, and we're going to be duplicating a real-world setting in a visual haptic environment. So we'll be directly comparing motion parameters from humans tracked in a real-world task with a Vicon system to the same task duplicated in the visual haptic environment. This allows us a baseline comparison of real world to visual haptic telepresence. Key thing here is that with our VR and telepresent environment, we are then able to introduce these transforms systematically. For example, translations between the workspaces, rotations between the workspaces, and scaling between the workspaces. And that will allow us to effectively kind of say, well, you know, maybe, for instance, we'll find that translations and scaling offsets don't really matter that much. They don't really impact performance that much in such an environment. But if we're imposing rotations between the physical and the visible workspace, this could be really detrimental. So the key idea here is that we are kind of taking an understanding of how the brain processes sensory motor information, parametrically manipulating these transforms, and in effect kind of trying to feed into how to, kind of manual, one could say, of how to design and best optimize a telepresence system. What does one need to get right, and what can one afford to get wrong? So, final slide. If you just take one message away from this, it is that with a human in the control loop of a telepresence system, it's completely essential to understand how the brain processes sensory information, how that sensory information is integrated and indeed compared to predictions about what the sensory output of our actions will be, and indeed how an observer or a user is able to adapt to these transforms over time. Cool, that's everything. Thank you very much for listening, and I'd be happy to take any questions.
That's great, thanks Peter. So if anybody has any questions, as I said earlier, please could you just type these in the chat box. I haven't had any yet, so we'll just give it a minute or two just in case anyone's typing. And again, a reminder to anyone who would like a link to the recording, just get in touch with the Brain Hub following the meeting, following the session even. Okay, we've got a question. You mentioned, sorry, my cat's just looked in front of the screen. Move back. Right, you mentioned iterative learning in your talk. To what extent, I don't know if that's how you say that word, is the iterative learning model from control similar to the learning model of a human? Does this relate to the sampling-based idea of human learning?
I'm not entirely sure what the sampling-based idea is, but in general, there's a very close correspondence between the two. So obviously, I've kind of come from a background of perceptual psychology, a trained psychologist, but I work in a kind of more engineering type area. And what I've found is there's actually a stunningly close correspondence between the way in which people such as us model neural processing and how engineers are modeling learning as well. So in answer to the first part, yeah, there's a very, very close correspondence. I'm not entirely sure what the sampling-based idea of human learning is though, so sorry, I might have to talk to you about that offline.
Another question. What again did you say was the gold standard for movement performance? So
from a kind of human motor learning perspective, there isn't really any a kind of a single idea about what classes a good movement, what is the gold standard. And there are a whole bunch of ideas about what parameters might correspond to efficient movement and indeed optimal models of movement production. So as a result of this, what we're doing is we are going to be measuring real-world human movements with our motion tracking system, and we'll actually be using those as the gold standard against which to compare the telepresent movements with our the transforms. And this kind of sidesteps the issue of the difficulty in actually defining what constitutes an efficient movement. Obviously, however, as I said, the ideal is that a telepresent system could actually enhance human movement. That generally isn't the case at the moment.
Okay, that's great. Thanks, Peter. We have got another question, but just because of the interest in time, I think we're going to move on. So I don't know if you could reply to that one in the chat page. If we've got time at the end, we can come back to it if that's okay.
Yeah, sure, no problem.
Great. So I'm just going to pass over to Inmo now. If you could start sharing your screen. Inmo, are you on mute?
Okay, can you hear me?
Yeah, that's great.
Okay. Oops. Yeah. Okay. Hi, I'm Inmo from University of Manchester. Today, my talk is about how to minimize worries in nuclear telemanipulation. So in ReinHub, actually there are two groups. So one of them is remote handling group. So I'm a member of that group. So the remote handling group has been particularly looking at using robotics and AI for the nuclear glove box tasks. As you can see in the left-hand figure, normally these tasks need human operators who are wearing protective suits and going into nuclear environments. Using glove box, they do some manipulation tasks. However, despite of the glove box and their protective suits, there are still some possibilities for the human operator to be exposed to radioactive materials, which may cause some issues like cost and safety. So to address this issue, the remote handling group is trying to use the teleoperated robotic system like this instead of the human workers. However, still there are many research questions in terms of how we can improve transparency between the operator side and the slave robot side, and how we can improve the overall system performance as well as safety. The system architecture that I am thinking of is so-called AI-assisted teleoperation. Basically, in this system, a human operator can teleoperate the robot as a typical teleoperation system. But on the other hand, there is another element, control element, which generates assistances depending on situation by sensing the environment. And by having such AI assistances, I believe that we can have better performance and safety. So given this context, what I have been investigating so far are twofold. The first one is about the user interfaces. Particularly, I have been thinking about what would be easy and intuitive and cost-effective user interfaces. And personally, I'm interested in using lip motion sensor by which we can teleoperate the robot, this kind of robot, with our bare hands, like this video. I believe this method is quite intuitive because in this demo, I just asked Dr. Andy Whiteman to try this system. And surprisingly, he was able to pick up this object without any training. And this is his first trial. And second topic is about how to get assistances from AI. So today, I will present about this one in more details, particularly how to achieve collision avoidance during teleoperation tasks. So let's imagine we are doing a teleoperation task. Without any obstacles, we will not feel any worries and we will be okay. However, if there are some objects that the robot shouldn't collide with, then this teleoperation task may require the human operator to be super careful. So this task could be like this kind of mission. So to minimize such human operators' worry during the manipulation task, the idea is to use a concept of virtual safety capsules like this. So these capsules make sure that the robot arm will not collide with the object inside the capsules, even if the robot arm is accidentally moving toward the capsules. So I believe this kind of safety feature is very important. For example, it could reduce, I think it could reduce human operators' psychological workload, and also it can reduce the gap between mock-up training and real nuclear operation. So then the questions are how to realize such a concept technically, and does it really reduce human operators' worry and improve task performance? So for now, I'm going to talk about my answer regarding the first question. And my proposed approach is to use optimization-based inverse kinematics and collision avoidance constraint. So here, please note that I assume that the system can recognize position and size of obstacles by using any computer vision technology. So before that, I'd like to mention some limitations of existing method for collision avoidance. So first thing is potential field method. So this method basically generates a potential field that guides the robot's end effector towards a safe area. However, as you see in this video, many of the recent works only consider the end effector's collision avoidance, not for the entire robot arm. So that's why this kind of the elbow can collide with this obstacle. So secondly, we might think of a null space-based approach. However, from our experience, it does not fully guarantee obstacle avoidance, and also it does not have any. I think that it does not have any allowance for us to add additional AI features. I will talk about it in more details later. And another way is to use sampling-based motion planner, such as OMPL in MOVEit in ROS. However, as you see in this video, and also from my experience, often it could end up with such aggressive movements. Also, often it takes time to obtain a full trajectory, so it does not seem to be suitable for real-time teleoperation. So our approach is to use a optimization-based inverse kinematics. Instead of using inverse Jacobian matrix for the inverse kinematics problem, we can formulate that problem as a optimization problem like this. One of the benefits of doing that is that we can include multiple desired features that we want the robot arm to behave by adding additional cost term here and also additional constraint here. So in this demo, the cost function includes the end effector's position and orientation matching and smoothness. Here, I put higher weight factor on smoothness for this bottom demo. So that's why the robot moves more slowly than the first case. So like this, depending on the weight factors and also the cost function and constraint, we can add some desired features into the robot arm's behavior. So based on such the optimization-based inverse kinematics, we can add the collision avoidance constraint. So let's say the space of the obstacle can be defined by multiple H functions. And also here, what we want is the robot position. Let's say this is robot position. The robot position should not belong to the obstacle space. So its physical meaning is that the H functions here are slopes of obstacle, and the obstacle space is the intersected area where all the H functions are positive. So this area. So then by following this kind of mathematics, now I'm not going to talk about its details. The original obstacle avoidance constraint, the condition can be reduced to this kind of equality constraint. So by applying this into the previous optimization-based inverse kinematics, we can have multiple benefits. So for example, the collision avoidance constraint can accommodate nonlinear shaped obstacles, and also multiple obstacles can be integrated into this single constraint. So for example, by having this type of H function, we can have polyhedral the obstacle shapes, or by having this, we can have ellipsoid, and also we can make this kind of complicated shape obstacle by having customized functions. And I tested this obstacle avoidance constraint by using a simple path planner based on the model predict control with a simple double integrated model. So from here, start point to goal, so you can avoid the collision, the obstacle, the collision with the obstacle. So now we are using this constraint to make sure that all the links, the entire arms, will not collide with the old capsules. So let's say we know the position of the capsules, and also we know the positions of two ends of each link. Then we can have these vectors from the geometry. And by using this formulation, we can compute the projected vector of W onto V. So here, this term denoted by S indicates the normalized size of the projected vector. So depending on the size of the value of S, we can conclude whether the capsule is in this area or this area or this area. So, and by having these conditions, we can get the closest point from the capsule towards the link, depending on the S value. And by doing so, we can consider the collision avoidance of the entire robotic arm. So to implement this approach that I explained before, so I basically use ROS, but a library, but I used a library called ROS-Rust, which is a equivalent version of ROS-Pi and ROS-CPP. The Rust is a quite new programming language. It's from the developer society. This language is considered as kind of challenger for C or C++ because it is fast enough, fast as much as C, but also it has other benefits such as automatic memory management and etc. And personally, the reason why I'm using Rust is actually I wanted to use this toolbox. So this toolbox is optimization toolbox called the OPEN. This is also a fairly new toolbox, which was developed for optimization of the embedded systems or robotic systems. So although this toolbox provides MATLAB or C++ or Python API, but from my experience, just using the Rust API is much faster than the others. So I directly use Rust. So that's why I use Rust as well. So in terms of implementing the obstacle avoidance constraint, we can have it as a hard constraint or soft constraint with very high weight factor. Obviously, if we have the hard constraint, it is expected that it needs more computation time. But soft constraint option will be faster, but may not guarantee collision avoidance. So I did some trade-off study between these two options. In this test scenario, I put multiple safety capsules, which are packed together so that they become like a wall. So here, each capsule's diameter is 10 centimeter. The radius is 10 centimeter. And the arm thickness from its skeleton was 5 centimeter. So the required collision avoidance distance from the arm skeleton is 15 centimeter. So let's see here. So this is the hard constraint option. So although it is supposed to avoid the obstacles theoretically, but in fact, the robot can go through the obstacles. Yeah, like this. So this is because in this setting, I had to set a parameter for maximum iteration for the optimization process. Otherwise, the output rate will be much lower than this. Actually, this value is still not good, but it could be more worse. And within this maximum iteration level, the solver was not able to solve the solution properly. So that's why the robot gradually went through the obstacles. So I tweaked the optimization process in a way that if the solver does not convert to the solution within the maximum iteration number, then the solver just used just previous solution. So now the output rate is still the same because it still uses the optimization process with a hard constraint, but the minimum distance, which should be ideally 15 centimeter, that is it is much better than before. However, still the output rate is not good, considering the fact that the UR5 it's the input subscription rate is the 125 Hertz. So I tested it with the soft constrained option. So in this case, I could get higher the output rate, but with some degraded collision avoidance performance. And I did a similar test with different scenarios where the robot arm is continuously moving and there are two obstacles. As similar to the previous result, the first case has poor performance in both output rate and minimum distance. And the second case, this one has almost a similar performance in output rate, but the improved collision avoidance. But here, as you saw, the robot arm could end up with abrupt behavior because as the solver, optimization solver maintains its previous solution, sometimes, especially when the marker is far from this end effector, the previous solution becomes kind of ill-conditioned initial gas for the optimization process. And third case shows that shows higher the output rate, but slightly degraded performance. And from these two tests, I conclude that the third option seems to be more practical than other two. However, we need to also have a look at the weight factors effectiveness. So I did so. So I did some trade-off study in terms of the weighting factors for the collision avoidance cost terms. So as we have higher weight factor on collision avoidance term, the output rate becomes lower, but the collision avoidance performance becomes improved. However, the marginal improvement is not that high. So considering the fact that the UR5 input subscription rate is 125, so choosing weighting factor of the 1000 seems to be reasonable. So now let's see the performance compared to the normal inverse kinematics. Obviously, the normal inverse kinematics does not consider the obstacle avoidance, whereas the collision-free inverse kinematics can slip over, slip through these surfaces of the safety capsules. So in summary, we propose a collision-free inverse kinematics method, which seems to work quite well. But we also should notice that the 50% of additional the capsule thickness should be considered. For the future work, this work still needs further rigorous analysis by having more randomized tests. More importantly, we also need to have user case study to look at whether a human operator really have reduced worries or reduced the workload when this system is being used. And I think the method can be used for other applications as well. For example, let's say this, let's imagine the robot arm in the human-robot collaboration workspace where the human worker is just walking around the robot. In that case, we can capsulize the human worker by this safety capsule so that this robot can avoid the human worker in this human-robot collaboration workspace. And also, as you can see in the second video, actually we can push the robot by using the safety capsule. So it also could show kind of potential to be used as kind of compliant replacement of the compliance control, because the UR5 doesn't have compliance control function inside. So maybe it could use for this. So thank you very much for your attention, and I'm happy to listen any questions and feedback from you. Thank you very much.
Thanks, Inmo. That's great. We are running out of time a bit, so just in the interest of time, if anyone does have any questions, if you could put them in the chat, and if Inmo, if you could answer any questions in the chat, please, so we can just carry on with the talks. So yeah, any questions? Inmo will answer in the chat, and Alex is up next. I'm going to be sharing his slides, so let's see if I can get this to work. Bear with me. Has that worked?
Yeah, that looks good, thanks. So hi everyone, I'm Alex Smith, I'm from the BRL. I'm actually working on the NTNR project rather than the RAIN project, but we are working on similar things and we've been trying to work on some collaboration as well. The NTNR team,
All right.
so I'm just going to present my user study that will be actually collecting data whenever we get back into normality, as I was just about to start before everything went to shit. So the team and NTNR team at BRL is Tony Pipe, who is now going into retirement, but Manuel Giuliani is the two PIs. Mehdi is working on the VR interfacing, so looking at remote viewing of robots in remote environments. Joseph started with us recently. He's working on using 5G for more reliable wireless for teleoperation, and Greg's working on mobile robot control as well. Just started his PhD. Next slide, please. We also have another project called RNE, Robots in Nuclear Environments, which we're working with some other partners as well, with the RAIN and other universities. Alan Winfield's the PI for that one, and we also have Paul Bremner's doing work on VR as well, doing characterization, showing environments in VR and sort of making it easier to visualize remote environments. Craig West has left us recently, actually, but he was working on swarm control, and Tom Bridgewater was working on risk analysis for robots in extreme environments as well. Next slide. So just an overview of what variable autonomy is when I'm talking about it, is we have a scale basically of going from a fully teleoperated control where you have a one-to-one control, almost like a manipulandum. And then on the other end is fully autonomous, where the robot doesn't have any input from the user. And in the middle, we can have things like assistive teleoperation with haptics, waypoint control, where you tell a robot to go and it automatically goes from point to point, and goal-based autonomy, where the robot, you give the robot a goal to do, and then it works it out autonomously how to carry it out. And the other thing I'm looking at is the control design for smooth switching between different levels of autonomy. So, for example, if we're going from, say, a driverless car, switching from a manual driving mode where the driver has full control to autonomous driving, how do you do the switching between those control modes so that the user doesn't get confused, or there's no issues with instability and that kind of thing? So we do next slide, please. So the hypothesis for my study is increasing the levels of autonomy in a task should reduce the cognitive and physical loading for the operator. And the way we're doing that, so go to the next slide. So my study setup is we have two mirrored teleoperation robots. These are Franka Panda arms, which we've been working with Lincoln University to develop the control for. And it's just a pile sorting task, so the user gets 6 objects in front of them, in front of the remote robot, and has to use a master robot within a line of sight to sort those 6 objects into 3 different bins. I will be running 60 participants first, mostly from people within the lab and with robotics experience, but then later on, hopefully have access to nuclear operators who would do this kind of task normally within their job. We're looking at, so the physical loading will be measuring the forces that are applied on the master end, and then cognitive loading will be based on NASA TLX questionnaires, and also physiological measurements such as heart rate and galvanic skin response. We'll also look at how the failure modes happen. So obviously within the nuclear industry, we want to minimize failures as much as possible. So see how we can identify those and work against them, and conduct user interviews as well, so that we can get a better idea of what the main problems with the control modes are. So go to the next slide, please. So within my study, I'm running 3 levels of autonomy. The first one is no feedback at all. It's a straight joint-to-joint mirroring of the manipulators. So when you move one, the other one moves exactly the same, and there's no feedback at all. So that if you hit an object or you hit the table or something like that, the master side won't be able to feel it. And then the second level is autonomy, is guided teleoperation. So objects within obstacles on the slave side will have a virtual force field placed around them, and there is also feedback if you touch the table. And then the last one is autonomous long movements. So the user carries out the more complicated part of finding an object and picking it up, and then uses a keyboard to basically tell the robot where to go. So go to the next slide, please. So measurements for cognitive load, just to give you a bit more of a detail on this one. Normally you use NASA TLX is the most common one, and the grading chart on the right-hand side is roughly how it works, where the user carries out the task. If we can go. When the user carries out a task and then fills in this scaling basically and then these scores are aggregated, and cognitive loading of the task is basically graded using this questionnaire. So if you go to the next slide, please. We're looking at also physiological measurements. So on the left-hand side, this is some data from a galvanic skin response. So this is basically measuring the conductivity and the resistance of your skin, normally with two electrodes placed against your fingers. And there's various ways of looking at the data. In this case, there's a number of peaks in the response, and you can count the number of peaks, and normally what the idea is, the more peaks that you get in the GSR is indicates more cognitive loading. And then there's also, on the right hand side, you can see there's a whole bunch of other different methods for doing physiological response, such as oxygen levels, eye tracking, skin pressure, and that kind of things. So I think if you can play the video now, Laura.
I'll try.
Yeah. So the video that hopefully we can see will be, this is the instructional video for my study, just to give you an idea of what the study looks like. So we're using something called the shimmer sensor, which does the galvanic skin response and heart rate monitoring. So the Velcro straps are where the GSR sensors sit. Unfortunately, there's a problem with this sensor is that whatever hand that the sensor's on is the user can't use. So I've had to design my study so that participants can do everything with one hand, as the heart rate monitor touches the earlobe. So this is the first condition where there's no feedback. You can see so the user has line of sight, so they have to worry about if they can see the objects or not. And then it's just simply picking objects up and putting them in the correct bin. There's a couple of small barrels in the way, which act as our obstacles for the study. And then the user uses a keyboard in front of them to open and close the grippers. So the participants are given as much time as possible as they like to carry out the study, and one of our measures will be how quickly it's carried out. So in this condition, there is a force field that acts around the barrels, and there is feedback through the table as well. So if they touch the table, they should feel it on the master side, and the task is exactly the same again. So you can see here, it's difficult to see in a video, but there is a force field acting around the barrels, so you can't touch them. So this is something related to Immo's work as well, is where the links of the robot can actually impact with the object. So that's something we could think about looking at. This is the third condition where it's more autonomy. So the robot moves into position, a tone is sounded so that the user knows that it's gone into manual mode. They move it to a grasping position on an object that they choose, and then they can pick a bin number using the keypad, and the robot automatically moves that position and drops the object. And that's repeated for all objects as well. So I think that covers my study at the moment.
Okay, do you want me to stop sharing that then? The video, or do you want it to continue, Alex?
Don't think there's anything.
Okay.
Yeah, you can stop the video now.
Okay.
Yeah, we can stop there now. So might as well stop. So that's when we we'll be carrying out. Hopefully we'll get some actual nuclear industry operators working with that as well, as we're interested in how we can make the operators' jobs easier rather than doing it in a fully lab setting.
Great, thanks, Alex. Again, we're kind of at the end of time, so again, if you've got any questions for Alex, you can put them in the chat. We do save a copy of the chat, so we'll be able to share the questions because we haven't been able to read them out. But I think Guido's just going to conclude the session. Guido, do you want to come back?
Right, yeah, thank you very much. I mean, there is very little time now left, but what was important to us to gain, obviously, not only feedback on the technical outcomes, obviously, we have here, but also feedback on the organization and the idea actually for the workshop. And I do appreciate that actually there is very little time, but if you could actually send some further feedback, maybe actually to John Jukes, but maybe actually voice out here within the next 1 or 2 minutes some kind of obviously form of ideas in terms of our workshop. We said actually it's a 3-day workshop, 2 days essentially at first. The first one actually dedicated to industry, giving us ideas about the future of HRI in industry. The second day on actually academia, theme-oriented actually talks. And then the third day with a bit of a gap in between for you actually to think about actually what we can discuss then together as a community between industry, academia, and also stakeholders from actually funders. What can we do actually beyond RAIN and NCNR and the other hubs actually on extreme conditions in robotics? So that would be really good if you could send actually some email actually to John Jukes or have some further feedback now. That would be really brilliant from you. And yes, also just to mention, John actually mentioned that we think of obviously more virtual kind of demonstrators for RAIN, and to show you, actually showcase some of our HRI actually outcomes and general outcomes of RAIN. And as you see, actually we have strong and good connections obviously to actually NCNR, which have actually grown also quite naturally. Okay, thank you very much.
Great. Thanks, Guido, and thanks to all the presenters. It was all really interesting. Just to let you know, next week on the 25th, we've got takeover by the Orca Hub. So if you can attend that, that should be something a little bit different. Again, I'll stay online for a couple of minutes just in case anyone does have any last-minute questions they want to add in the chat. But otherwise, thank you very much for joining us today, and yeah, hope to see you soon.